Okay, so we are working on this boundary value problem using an inverse method. We've written out, we've decided to consider a case of simple shear, right? We've written out the kinematics, and for the case of an isotropic hyperelastic material, we have also written out the general form of the Cauchy stress. Okay, and that general form I have reproduced for us and copied the very last slide that we wrote out from the previous segment. The general form of sigma appears at the bottom. Okay, and I've written it out in matrix notation to point some things out to you. Okay, observe in particular that we started out with simple shear, right? Yet, if you look at this final matrix form for the Cauchy stress, you will observe that in general, okay, in general, the what you would otherwise call the normal stresses, right, the 1, 1, 2, 2, and 3, 3 components are decidedly non-zero. Okay, right? So let's make some observations, right? So note or notes. Okay, if you compute sigma I, okay, and here we have sigma I being defined as EI dot sigma EI. Okay, no sum on I here. Okay, which means really we're considering the II component, right? This is not the trace, we're really considering just the II component right now. Okay, so what you will see is that sigma 1, 1, okay, is clearly not equal to 0. Okay, and that is just the 1, 1 component of that matrix form of the stress tensor. Okay, likewise, the sigma 2, 2 component is not 0. Sigma 3, 3 is not 0. Okay? So here you have a situation where we have a simple shear problem, right? The kinematics that we've chosen is the kinematics of simple shear. Right? And we did that, right? We did that properly by saying that F has this form. Or even more, even going even further back by saying that the displacement field has that form, right? So we're specifying that the displacement is all along the E1 direction. But when we consider a rectangle of that shape, we saw that the effect of the displacement is essentially to shear it, right? That is U, right? Okay, even still, what nonlinear elasticity tells us is that these normal stresses are not 0. Okay. Also, if we consider the hydrostatic stress, okay, which is 1/3 trace of sigma, okay, it also is definitely non-zero, as you can see by going back to that slide. Okay, so these kinds of effects that we are seeing arise from the fact that we have nonlinear deformations here, right? And we've properly, in fact, exactly accounted for nonlinear deformations through the theory we've constructed over the past many segments, okay? This effect, where even the kinematics of simple shear gives rise to non-zero normal stresses and therefore a non-zero hydrostatic stress, is an effect called the pointing effect. Okay? It's actually quite easy to show why this should exist, and we can show it with this little figure that we have right here. For finite shears, right, so shears which are defined by gamma being finite, right, not infinitesimal, what happens is that that fiber gets stretched out. Okay? When we shear a rectangle, right, or a rectangular block along one of the axes, if gamma is large enough, right, we do have stretching of fibers. Okay? And what this means is that there does indeed develop a traction on that surface. Okay? Right? And now this can be expressed by the fact that we may ask ourselves, okay, what do we do about boundary conditions now? Okay, we can now follow this inverse method where we have all the fields that we need. We have the kinematics as well as the stress fields. We can now go back and ask ourselves, well, if we want to sustain this type of a simple shear deformation and the stresses that arise from it, what do we need, right? So this is not too difficult to do, right? So what kind of boundary conditions would we need to sustain this? Okay. We could say now that on the surfaces, right? So let's suppose that we say that partial of gamma naught u, okay, consists of the following planes, right? It includes the plane x let's x2 equals should we say x2 equals 0? No, let's go with x1 instead. Let's suppose that we say it includes the surface x1 equals 0, x1 equals L, right? Where with E1 and E2 aligned as shown, right, on the reference configuration, right, we have this distance is L. Or perhaps we better call it L1 because we're going to need things for the other directions also. Okay, so that face is x1 equals 0. That face is x1 equals L1. Okay, all right. So that is our displacement boundary. Okay, and now we know what the displacement field is on those boundaries too, right? Because we started out by choosing the displacement field, right? So on that displacement boundary, our condition is that u is specified, right? It's a specified function, depends upon x, and in particular, it's gamma, right? A constant, times the x2 coordinate on those surfaces, right? So at every point on that surface, we know what the x2 coordinate is. We evaluate the x2 coordinate, it's that, in the E1 direction. Okay, so that's the displacement field we are specifying. Okay, and then we can say that really the traction boundary is everything else. Okay, right, so the traction boundary is the entire boundary from which we take out the parts that we've defined to be the displacement boundary. Okay, and that's what that backward slash means. Okay, you can literally think, sometimes people write it as, some authors choose to simply write it as partial of omega t minus partial of omega t u. Okay, it's everything else. right? The other boundaries are all traction boundaries. Okay, so what this means then is that we have partial of omega t is everything else. It's that boundary, it is that one, it is this one, and it is also the one that is on that surface. Okay, all of those make up partial of omega t. All right, and on those boundaries, we, as usual, we say that, well, on those parts of the boundary, right, we're saying that we need to say what that field is, right, where P is the first Euler-Kirchhoff stress tensor, right, and N is the unit normal to those faces, but we know what each of those unit normals is, right, because it's a nice rectangle, right. So those unit normal N just takes on the values either E3, plus or minus E3, and plus or minus E2, right. Right, so on these faces, N equals plus minus E2 or plus minus E3, right, depending upon which of those faces we pick. Okay, so if Pn is the field we need to specify, we need to say what it is. Well, this is easy enough, right, because we already know actually what P is, right. Okay, so we know what P is because we know what sigma is, right. So P is just 1 over J sigma, which we have on the previous slide, F inverse transpose, which we also have. Okay, so effectively what we're saying is that, well, this is specified to be what we have from the stress field already, right. So this was the boundary condition that we need, okay, to sustain this field. Okay, so really we've done this all in inverse, right? We found out the field, we found out the stress, and we said, okay, what do we need to sustain it? Well, we know how to calculate this boundary condition now. Okay, so these are the boundary fields that you will need to sustain this particular type of deformation, this particular type of stress. And as you can imagine, if you were to go ahead and compute what P is, you would indeed conclude that. Okay, so this is an easy check, which I will leave for you to do. You can easily check that P11, P22, P33 are in general not equal to 0, okay, for this case. So what this says is that you take a rectangular block, right, you plan to shear it, right, you plan to give it a deformation which you understand to be simple shear, but in order to do that, right, you do indeed need to provide tractions on these surfaces, okay, you do need to provide tractions here, right, likewise on this surface as well, you do need these tractions, okay, and this all comes about from the fact that in the deformed configuration, right, in the deformed configuration, what we have a stretching of fibers, and it's most notably seen for that diagonal fiber. Okay, right, the fact that this fiber, which started out being that long, has now got stretched out to more under the deformation, under the shearing deformation, is what gives rise to the need for tractions in the perpendicular directions, in the normal directions, in order to sustain that simple shear. Okay, so the message is that nonlinear elasticity says that right, it says that normal stresses to sustain, right, normal stresses are needed to sustain simple shear. Okay? In contrast with linearized elasticity, which is based upon the infinitesimal strain. right? For linearized elasticity, what you would conclude is that the infinitesimal strain tensor, right, epsilon, is this. Sorry, I don't have gamma. I have a gamma here as well. Okay, this is the infinitesimal strain tensor. Okay, and then if you went ahead and computed sigma equals C contracted with epsilon, okay, where you used your linear elasticity modulus, for isotropic materials, right? And we know this object very well, right? If you were to go ahead and compute this, what you would see is that sigma is this. Okay, no normal stresses, right? No hydrostatic stress, okay, but decidedly wrong. All right. Okay, so there's a story that I've heard that Poynting was, I guess, an engineer, or he wasn't one of the high authorities in mechanics, and when he realized this effect, he took it to Saint-Venant. Saint-Venant who was at the academy in Paris at that time, was all about linearized elasticity, and his theory did not admit the result that Poynting found, so he dismissed him. So anyway, that's the story. So okay, so so much for this segment. We have one more thing to do here, which is look at how nonlinear elasticity reduces properly to linearized elasticity with infinitesimal strain, but that will be in the next segment.